In this video, we're going to talk about the basic differentiation rules and some of the subtopics that would come along with it. So first, let's recall what the tangent line is, because for differentiation, it's based on the tangent line problem. So the tangent line problem, the tangent line is a line that intersects a circle at exactly one point and is also perpendicular to our region. So for example, if we are to draw a circle, say for example we have the circle, in geometry this line that will touch the circle, although it looks touch at different points, but it's supposed to touch only at exactly one point. Okay, let's redraw that. Okay, there you go. Say for example, let's just draw it here. Yeah, it's better. That point here is the point of tangency, and this line here is what we call our tangent line. So there. Now, since it's a circle, it will just really touch at exactly one point. It will not pass through any other part of the circle. And you can make it that way also, that you can draw a tangent line that will not pass through any other point. However, for a general curve, it becomes more difficult because, for example, if the curve is like this, it's easier. But if curves like these, it might be more difficult because we do not know where the extent of our graphs may be. For example, in this graph here, it's tangent here, but once you extend the line, it will no longer be a tangent line. So, essentially, the problem of finding a tangent line at a point P boils down to the problem of finding the slope. Because if you remember, for a line, in its equation, we would need the slope and the y-intercept. In the slope-intercept form, which is usually the form of our function, f of x is equal to mx plus p, this b, which is usually our y-intercept, can just be from any point on the graph. Which means it will boil down to what would be the slope now of our tangent line. And we can approximate the slope of the tangent line using the slope of the secant line here. We know from analytic geometry that the slope of a line given 2 points is given 2 points x sub 1, y sub 1, x sub 2, y sub 2 is given by the formula y sub 2 minus y sub 1 over x sub 2 minus x sub 1, usually remembered by rise over run. In this specific figure here, we can see that from the point C, let's, instead of doing that, maybe we can remember it this way. So now, instead of y sub 1, y sub 2, we now have the points C, f of c, which becomes our x sub 1, y sub 1, and c plus delta x becomes our x sub 2, and this is our y sub 2. Because now we are on the language of functions. So as we can see here, it's c and then c plus delta x, because that's the change from c to this point. From x sub 1 to x sub 2, that distance or that change is delta x. And that change in y from y sub 2 to y sub 1 is delta y. So that's why we can then see that we can write the slope as the change in y over the change in x. The triangle delta, or the delta symbol, would mean change. So with that in mind, if we are to replace these coordinates in the formula for the slope, what we're going to get would be the slope of the secant line. The slope of the secant line would be f of c plus delta x minus f of c, that's y sub 2, y sub 2 minus y sub 1, all over x sub 2, which is c plus delta x, minus x sub 1, which is c, which cancels out c. Therefore, the slope of the secant line will be f of c plus delta x minus f of c over delta x. And this side of the equation is known as the expression, the difference quotient. So this will be now the basis. This is now the slope of our secant line. One can obtain more and more accurate approximations of the slope of the tangent line by choosing points closer and closer to the point of tangency. As we can see in this GIF, the closer the 2 points together to the assigned point of tangency, the more accurate the approximation of the slope of the tangent line would be. That would mean that as the change in delta x from one point to the other, as we have pointed out a while ago, delta x, the change from x sub 1 to x sub 2. As delta x, the change from x sub 1 to x sub 2, gets closer and closer to 0, meaning there will be no change, it will just be 1 point, the limit of that becomes the slope of our tangent line. Hence, the definition of the tangent line with slope m. As follows: if f is defined on an open interval containing c, and if the limit of delta y over delta x as delta x approaches 0, which is equal to the limit of f of c plus delta x minus f of c over delta x as delta x approaches 0 equals m exists, then the line passing through the point c f of c with slope m is the tangent line, the graph of the point c f of c. That's why we can also call m the slope of the graph, not just the tangent line, but it's the slope of the graph at x equals c. Now, the definition of a tangent line to a curve does not cover the possibility of a vertical tangent line, because for a vertical tangent line, it has to be infinite limits. As shown, it can be somehow thought of, not really somehow thought, but it's very similar to a vertical asymptote, but this time it's a vertical tangent. So if f is continuous and the limit of the difference quotient as delta x approaches 0 is equal to positive or negative infinity, then the vertical line x equals c that passes through c f of c is a vertical tangent line. Now further, in relation to the tangent line, we have the normal line. The normal line is a line perpendicular to the tangent line at the point of tangency. So one thing that we would have to do here is to find, if you're asked to find the slope of the tangent line, might as well find the actual equation of the tangent and later on the normal line. So let's have an example here. We're asked to find the equation of the tangent and the normal line of the function f at the given point. So let's start with number 1. With number 1, we are given with f of x is equal to 2x squared, and we're asked to find the equation of the tangent and the normal line at the point negative 1, 2. So to find the slope of the tangent line, we have to find the limit. And going back, it's this limit here that we would need to get. So therefore, we would need to find the limit of f of c plus delta x minus f of c all over delta x as delta x approaches 0. Given that f of x is equal to 2x squared, we follow that. So this now becomes the limit as delta x approaches 0 of 2 times c plus delta x squared minus 2c squared over delta x. And we need to first simplify the difference quotient here before we can find the limit. So therefore, we're going to have as limit of delta x approaches 0 of 2. Then we expand this. This becomes c squared plus 2 delta xc plus delta x squared minus 2c squared all over delta x. So from there, we have to distribute this 2 here. So we're going to have the limit as delta x approaches 0 of 2c squared plus 4 delta xc plus 2 delta x squared minus 2c squared over delta x. So we can cancel out the common terms here because that's 2c squared minus 2c squared And this now gives us, oops, sorry, here, sorry about that. There you go. So we now go to here. This becomes now the limit as delta x approaches 0 of 4 delta x c plus 2 delta x squared all over delta x. As we can see, we have a common factor of delta x. So we'll have the limit as delta x approaches 0 of delta x multiplied by 4c plus 2 delta x all over delta x. This gets cancelled, therefore, we get the simplest form of the limit as delta x approaches 0 of 4c plus 2 delta x. And now we can apply our limit theorem of direct substitution, and we're going to have 4c, which then implies that the slope of the tangent line, is given by the expression 4c. So the slope of the tangent line at the point, the slope of the tangent line at negative 1, 2 will be given by 4 times negative 1 is equal to negative 4. So with that, we now have a slope of 4, negative 4 rather, and a point at negative 1, 2. So we can now use the point slope method to find the equation of the tangent line. So therefore, we're going to have y minus 2 is equal to negative 4 times x minus negative 1. That turns to x plus 1. And 4 times x plus 1. So to find the equation, I'm going to write it in slope-intercept form. Let me first distribute the negative 4 on the right hand side. That becomes negative 4x minus 4. Transpose, we're going to have y is equal to negative 4x minus 4 plus 2, which gives us the final equation of the tangent line. Y is equal to negative 4x minus 2. There you go. Now, for the equation of the normal line is perpendicular to the tangent line. And as we know, the slope, since the normal line is perpendicular to the tangent line, the slope of the normal line will be the negative reciprocal of the slope of our tangent line, which would be, in this case, that's negative 4. Here's I'm going to have negative 1 over negative 4, which gives me 1/4. So the slope of the normal line is 1/4, but it still passes through the point negative 1, 2. So applying the same technique of finding the using the point slope form, we're going to have y minus 2 is equal to 1/4 times x minus negative 1. That becomes x plus 1. So I'm going to distribute first the, since this is 1/4 multiplied to this, I can multiply both sides of the equation instead by 4 to make our life easier. Therefore, this becomes 4y minus 8 is equal to x plus 1. Sorry, since we're going to turn this into slope-intercept form, I should not have done that. So let's recall that. What would I have done instead? That's what you do if you're going to write it in standard form. But since I would like to have it still in slope-intercept form, I should have just distributed 1/4. That becomes negative 1/4 x plus 1/4, and then transpose 2. I'm going to have y is equal to 1/4 x plus 1/4 plus 2, which is 8 over 4. Therefore, the equation of the normal line becomes y is equal to 1/4 x plus 9/4. There you go. And as you can see, it's quite a tedious process in finding this, in finding the expression that would give us the slope of the tangent and later on the normal line. So, we would have now different rules to make the process easier without going through the limits. And we'll go through that in the next video.